right, thank you, Dawn. Is the volume okay? Not too loud, I'm not, okay, good. All right. If I start screaming, just let me know, because I get excited about planet formation. It's a pleasure to be back at the Sagan workshop. And as Dawn said, we did a little bit of rearrangement. So what I'm going to try to start you out with is kind of a basic primer on the physics of planet formation. And I'm going to leave it to Jan to tell you more about the actual populations of planets and how these different mechanisms work together to maybe produce the things that you're observing. So this talk is not going to cover necessarily all the different types of planets, but really what are some of the underlying mechanisms that we think are really important for forming planets. So just a quick survey. How many of you took in graduate school a class with planet formation in the title? Okay, good. So hopefully this won't all be total review for you, but in that spirit, I hope you will interrupt me as I go along, and Dawn won't get too mad at me for doing that. Good. If you have questions or if something I say doesn't make sense. Okay, so let's get started. So just to sort of put us in the right frame of mind, I thought I would begin with some of the sort of big challenges we have as we try to understand planet formation. Obviously, exoplanets are in many ways an observationally driven science, but for this particular problem, we have some issues that we have to contend with. The first one, of course, is that planets form from a sort of small by mass component of the disk. So think about what you heard yesterday, for example, about metallicity, right? Almost everything isn't metals. And if we think about what we inherit in our star and planet forming system from the ISM, we start out with a gas to dust ratio of 100 to 1. So the stuff that we're looking at that's going to make our planets is a tiny, tiny fraction of everything else that's there. More importantly, we can't actually directly observe the particles at some of the most crucial stages of planet formation. Recall that particles emit most efficiently at their own wavelengths when we're talking about cold things. So micron-sized grains emit in micron wavelengths, millimeter and centimeter emit in millimeter and centimeter wavelengths. And if you say wanted to observe meter size, 100-meter size bodies, you're kind of out of luck. We just can't do that. And they're tiny, and they're dark, and they don't emit a lot of light. Think about how difficult it is to observe Kuiper Belt objects and asteroids in our own solar system. We just don't have that technology. So we're somewhat limited in what we can directly see. On top of that, solid and planet gas interactions are quite complicated. So there's a lot of different pieces of physics we have to keep in our heads as we're trying to understand these models. And perhaps most confoundingly, planets are not well behaved and they don't live where they were born necessarily. Which means that when you all go out and you find these great populations of exoplanets that are evolved, I can't say, well, there's an Earth at 3 AU and a Jupiter at 6 AU and also at 0.1 AU, so I have to be able to make them at those locations. We know that they move around, they migrate, they scatter, and I know both Jan and Elisa are going to talk a lot about that later on this afternoon. And so that makes it more difficult to do that sort of backwards extrapolation that would be so easy from the systems that you actually observe. A few more words of caution for things that focus on microlensing planets. And this is something that's come up a lot, is that we're talking primarily about M-dwarfs if we're talking about microlensing sources, and that's not necessarily what most planet formation models have been built around. So for example, disks. A lot of these standard stories you might hear about protostellar and protoplanetary disks originated from Herbig AEB stars because they're bright and easy to see. So keep that in mind when you're assuming something about a relationship you might be reading about. The exoplanet samples are somewhat sparse in the M-dwarf regime, although that's getting better every day. And of course, the sort of fiducial scaling that you will see in theoretical papers is oftenly for a solar-type star. And one thing you should be careful of is if you take some paper and you're flipping through and you find the place where they say, aha, planet mass scales like something times M star over M sun. You can't just substitute a half solar mass or a third of solar mass into that model without carefully reading that paper and understanding what other assumptions went into it that might have controlled that prefactor out front. Right? M-dwarfs have different spectra that can change the chemistry, that can change sort of where things happen in the disk. And so we can't just naively extrapolate down to M-dwarfs. So these are all things that we have to keep in mind. And just to give you a sense of this, this is I listened to Kaitlin's talk yesterday, so I did my homework and I went and made a plot on the NASA Exoplanet Archive. So this is sort of a pseudo HR diagram with stellar temperature on the x-axis and stellar mass. They didn't have luminosity on the y-axis. And you can see that this is not where most of our actual targets are yet. So we're kind of down here on this tail. So I just thought that was a nice way to illustrate it. Okay, so now for the outline. So what I'm going to do today, or at least attempt to do, is give you a quick review of sort of the standard old planet formation model, core accretion, as it was devised in the 80s and 90s. And then I'm going to focus on the newer developments in the last 10 to 15 years that address some of the classic textbook problems. And I say classic textbook problems, but actually I kind of mean the overused proposal paragraph problems. So some of the things I'm going to talk about are things that you still will see in an observing proposal or a theory proposal where they say, there's this classic problem with planet formation and we don't understand it. I want to try to show you some ways that we have in fact made progress as theorists in the last 15 years. So I hope you will agree. Of course, that doesn't mean we've solved everything. There's still a lot of things we don't know. And at the very end of the talk, I will spend a few minutes on the role of gravitational instability, and I hope I'll convince you by the end of why most of my time is going to be spent here and very little of my time is going to be spent here. Okay, so the classic core accretion model has a few different parts. So it's a so-called bottom-up formation model where we start with little things and we make big things. So in the classic core accretion model, we start with dust grains that protoplanetary disks inherit from the ISM, probably from AGB stars in large part. And they start out primarily at maybe micron sizes, and then they have to coagulate and grow together to become millimeter, centimeter, maybe even meter sizes. Now what I'm showing here is a relatively modern coagulation experiment where various groups will take different types of dust grains and put them in a drop tower experiment to simulate low gravity and try to understand exactly how they stick together and at what velocities. And one of the things I'll come back to is how difficult this process of coagulation actually is. You know from personal experience that throwing grains of sand together or pebbles together, it's very hard to make them stick. It turns out that even making them icy and putting them in low gravity environments doesn't really solve all those problems. But nevertheless, that is the picture in the standard core accretion model. You go from micron-sized grains and you coagulate through collisions. You get bigger and bigger and bigger. The next step is to just somehow keep getting bigger and bigger and bigger and ascend not from just microns to centimeters to maybe meters, but meters to 10 meters to 100 meters, and up until you get to things that are kilometers in size. And then we change the name and we start calling them planetesimals. Now, I haven't given you a theory for exactly how this works. And again, in the classic model, this is really just a series of collisions, and it's often just called coagulation. And again, I'll talk more about why this is a big problem. But let's just say, in the classic model, we somehow get these things that are planetesimals, things that are kilometers to a few kilometers in size. Once we get to kilometer-sized planetesimals, things get a little bit easier, because kilometer-sized bodies and up are big enough that they can gravitationally focus one another and grow through collision. So you can get these large bodies smashing together and increasing in size. And so this process proceeds, and there's been a lot of sort of theoretical work on exactly how it proceeds, whether the largest bodies grow fastest, and I'm not going to get into those details, but just think of it as gravity-assisted collisions. And these gravity-assisted collisions basically will make the cores of giant planets and terrestrial planets. Things get up to a few Earth masses in size, we think. And the final step in the classic model is that some of these planetary cores, if they get big enough, can undergo runaway atmospheric growth, where they have a sufficient amount of mass that they can actually attract in that hydrogen and helium from the background protoplanetary disk and grow into things like Saturns or Jupiters. So that's the classic core accretion model. Do any of my other planet formation friends in the audience want to comment on any other aspects of the classic core accretion model, or you're happy with it? Is Jan happy with this as the classic model? All right, he's happy with it too. Good. Okay, this is where things were left in the late 90s, I would say. And again, if you read a lot of proposals, some people seem to have stopped reading papers in the late 90s, and I'm not sure why. And many people will then say that the big problems in that classic model are as follows. 1, growing up to meter-sized bodies via coagulation is difficult. This is what I alluded to before. If you take small things that can't gravitationally focus one another in a protoplanetary disk, we can calculate their relative velocities, how fast they should be moving relative to one another, based on the background Keplerian shear in the disk, and with some assumed amount of turbulent motion. And even if you make that turbulent motion very, very small, the relative velocities of things are very fast, meters per second. And if you smash two things together at those velocities, they will typically bounce or fragment. So you take two things, you want to make them bigger, you smush them together, and maybe half of them sticks and the other half gets broken up into smaller things. That's bad if you're trying to grow over 12 orders of magnitude in size to make a planet. On top of that, there's the so-called meter-size barrier, and I'll explain this in detail in just a moment. And what this refers to is that when you get things to about a meter in size, even if you skip past this coagulation problem, they tend to just fall into the star really, really fast. And I'll explain why that happens in just a moment. But that's what people say when they mean the meter-size barrier. And then the final problem, and this is one that has become sort of a trope of problems with forming wide orbit planets, is that it takes longer than the disk lifetime, a few million years, to build up a core that is massive enough to suck up that big hydrogen and helium atmosphere. So we observe protoplanetary disks. We know that the gas goes away on timescales of a few million years. If I want to make Jupiter, I have to get my core grown quickly so I can eat up all that material. This problem isn't so big for terrestrial planets because they don't have a primary atmosphere. That's fine, but for the gas giants, it's a big problem. And as with most things in disk physics, the time scale will scale with the disk dynamical time, i.e. the orbital time. So short orbits have short dynamical times, wide orbits have long dynamical times. So these are the classic problems. And if you don't want to hear the detailed solutions, this is sort of a summary of all of the updates that we've had sort of in this century. So the first update is that we now have strong observational evidence that dust grains grow early. They do coagulate to some extent early to centimeters, millimeter sizes, and that they can be aided in growing early by things called pressure traps. We think planetesimals form via the streaming instability, which instead of being a bottom-up instability is top-down. It means we get to take those centimeter-sized bodies, and instead of having to step them from centimeter, meter, 10, 100, 1,000 meters, we can go from centimeter-sized bodies, crunch them all together, and get things as large as 100 kilometers in one go. Planetesimals then accrete, not just by colliding with other kind of equal-sized bodies or things that are not very different in size, but they can actually eat up small bodies really, really efficiently. So if I give my disk a 100-kilometer body, it then eats so-called pebbles, centimeter-sized bodies, tens of centimeter-sized bodies, really, really efficiently. And this drastically decreases the growth time of cores. And finally, one thing I just wanted to mention, but I'm not going to spend any time on later this talk, is that while the runaway growth phase isn't necessarily ruled out, we now think that planetary cores that become gas giants probably undergo gas accretion fed by a circumplanetary disk, and this is something that observers are trying to pin down now. Okay, so that's sort of the rough overview of what I would say the big changes have been in the last few years, and now I'm going to try to give you a quick understanding of why all these things might be true and give you a sense of what those physical mechanisms are. So in order to do that, the first thing we need to understand is radial drift. So how many people have sort of heard this term before? Okay, a lot more of you. Good. All right, but for those of you who haven't, we're going to start from the beginning. So again, if this doesn't make sense to you, stop me, because if we don't understand this, the rest of the talk is totally useless. All right, radial drift. So let's consider our standard protoplanetary disk. We often think of this as just being one kind of blob of stuff, but it's better to think about it as actually two fluids or two different sets of things. There's the gas, and then there's the dust. Now, gas feels pressure, okay? And so while we often refer to all the velocities in protoplanetary disks as being the Keplerian velocity, that's not quite true. So if I look at my gas going around in the disk, I would normally think about it as orbiting at the Keplerian velocity, square root gm over r. But it feels pressure. And disks tend to be hot on the inside and cold on the outside. So there's a decreasing pressure as you go outward, so a negative pressure gradient. And what that does is it sort of opposes the force of gravity. So the star is pulling in, making things try to go around at the Keplerian velocity, but pressure, if you have high pressure on the inside, it pushes things out. And so it pushes back against gravity, and so gas in protoplanetary disks actually orbit a little bit slower than square root gm over r. Okay, but particles, dust, is a pressureless fluid, right? Dust grains, planets, rocks don't feel pressure, and so they want to orbit at the normal Keplerian velocity. And so I've got my gas that's kind of chugging along a little bit slow, and then I have a rock or a dust particle that's trying to zoom through that gas at the Keplerian velocity. And so dust grains, rocks, and planets, they feel a headwind. So they feel gas dragging on them, right? And so that's what's trying to be illustrated here. The way that we try to parameterize this feeling of drag is through something that's known as the stopping time. And you can see various expressions for stopping time written down here. I've put them here in case you want it as a handy reference. It's not too important what the form is. You should just know that this is basically telling you how long it takes the gas drag force to slow down the particle to be orbiting at the same speed as the gas. And it, of course, depends on the properties of gas, right? This is something you know from riding a bike, right? The speed at which you ride your bike determines how much of a headwind you feel. If you're wearing a big puffy jacket, you feel a stronger headwind than if you're wearing a sleek spandex bike suit. And so in terms of disk properties, it depends on the density of the solids, rho s, the density of the gas, the size of the particle A, the sound speed in the disk, cs, and then lambda here is the mean free path, which is just 1 over the gas density. So in disks, we have this parameter here that's telling us how strong the headwind is. And since theorists like to use dimensionless numbers, we turn this into the so-called stopping time or Stokes number by multiplying by the dynamical time omega. So if I have a really, really tiny micron-sized dust grain, it's going to feel a really strong headwind. The gas is just going to slam on it so hard that it just wants to orbit right at the Keplerian velocity. It doesn't have enough inertia to fight back against what the gas is doing. And so that's this case here, where the stopping time is really, really quick. It just immediately goes and orbits with the gas. If I have a planet, right, planets are big. They have a lot of inertia. So the headwind doesn't do anything to them. They are in this limit where the stopping time is really, really long. They just blow through the gas unconcerned. It's these particles right here in the middle where the stopping time is of order unity that are most strongly affected. They don't just blow through the gas. They don't orbit with the gas. They get their angular momentum sapped by the gas, and they end up falling into the star. So that's what these different size arrows indicate. Tiny particles stay coupled to the gas. Really big things don't care about it. And things that are just the right size feel a very strong headwind, and they drift into the star. And what this plot here on the right is showing you is as a function of a semi-major axis in the disk, how long it takes things of various sizes, 1 meter, 3 centimeters, a millimeter, a kilometer, how long it takes them to fall into the star. And this is where that meter-sized barrier comes in. You see that meter-sized bodies have extremely fast drifts, right? They fall into the star in 100 years, 1,000 years. So even if I solve all of my problems with sticking things together, and I make a meter-sized body, if I put it in my disk, 100 years later, it's going to fall onto the star. So that's bad, right, if I want to take those things and make planetary cores. So this is the sort of basic physics that underlies a lot of what we now understand about planet formation, is this radial drift problem. Now, there's one thing that we now know can help us keep particles from just falling into the star, and these are so-called pressure bumps, okay? So this whole radial drift thing, right, all of it relied on the fact that there was high pressure on the inside, low pressure on the outside. You can think high temperature, high density, low density, and that was pushing back against gravity, causing the gas to orbit at a sub-Keplerian speed. So the particles felt a headwind. But if I have some special localized region in the disk where I have a bump in that profile, I can trap particles in one place, because stuff on the outside of this bump, where the pressure gradient is still negative, is going to drift this way. But the exact opposite process is going to happen along this curve, where the pressure gradient is reinforcing gravity, and it's making the gas orbit at super Keplerian velocities, and that can cause things to want to drift inwards. And so we can get these clumpy regions where we get extra density of particles. We go way above that standard 100-to-1 ratio we started out with. And this can really help coagulation models, because we get more particles in one region to collide and grow. And you might say, well, isn't this kind of arbitrary? You just randomly put a bump in the middle of your disk. Why shouldn't disks all be radially smooth? It's a good question. But in fact, there's lots of reasons why disks shouldn't be radially smooth, right? I started by saying, well, we can think of the disks as having two components, gas and dust. But of course, gas is made up of lots of different things, right? And gas has different phases. All these other molecules have different phases. So for example, at ice lines, we can have sharp changes in the gas composition as things sublimate, for example, or as things like CO freeze out onto grains. And this can create bumps in the disk. This model I'm going to show you on the next page by Palapania shows what can happen at a dead zone boundary. And a dead zone boundary refers to a place where we change sort of how material is transported due to magnetic fields. I don't have time to get into the details of it. But that's another thing that can create a pressure bump, because we change a physical process in the disk. And what she's showing here is as a function of semi-major axis, the grain size measured in centimeters, and the density. And you can see right here where this pressure bump is, we have a higher density and larger grains being generated in the disk. And so we think these pressure bumps may help sort of kick off the process of planet formation by allowing particles to coagulate to these larger sizes more easily. And for the observers in the audience, there's good news, of course, which is that we've actually observed these grains. They do exist. Right? We observe protoplanetary disks at centimeter and millimeter wavelengths. And I'll show you in a minute that we actually see some substructures that might be due to pressure bumps. So what I'm showing you here in this plot from Najida and Kenyon, it's a little bit complicated, but this is indicating not only that we have millimeter and centimeter sized grains, but that these grains have to grow pretty quickly to relatively large sizes where we can't observe them in order to explain the observed exoplanets. So this is the cumulative fraction of disks with a given amount of mass in dust. So very few things are measured to have even 100 Earth masses of dust. Many things are measured to have only a few Earth masses of dust. This green curve here shows you the cumulative distribution of Kepler actual exoplanets. So if I just take all the mass in Kepler systems and add them up, this is what that green line is. This blue line here, the cyan line, that's showing you class 2 disks in a young star-forming region. If you just look at these open square points here, this is the amount of mass you infer should have been in the disk if you include not just Kepler planets, but also microlensing planets in the data. And this is saying if I was 100% efficient in converting the solids in the disk into planets, I would need this much mass. And you can see these things are kind of right on top of each other. And we know planet formation isn't 100% efficient. We don't take every single dust grain that comes into the disk and store it in a planet. And so what this is telling us is not only have grains already grown to be the sort of centimeter and millimeter sizes that we observe, but many of the solids in the disk must already be even bigger of that and hidden in the disk in order to be able to explain how those disks can produce the exoplanets that we observe. And it turns out that the microlensing sample is really key because you're actually probing the outer parts of the disk, by which I mean things beyond an AU, right? It's, you know, the radial velocity planets have gotten out beyond an AU too. I'm being a little bit facetious, but But microlensing is really, really crucial for being able to probe sort of the normal solar system scales in exoplanetary systems. So I said that we not only observe the particles, but we may actually be seeing consequences of radial drift and pressure bumps in the form of these ringed structures. So I'm sure everybody's seen this beautiful image of HL tau, and the standard thing that everybody wants to tell you is that, oh, these holes are made by planets. Maybe they are, but in fact, even if these holes are made by planets, these bright rings that you're seeing are places where if there's a planet there, the planet created a gap, and then it created a pressure bump, and then that pressure bump trapped the particles. So even if there are, in fact, planets making these rings, and plenty of people have made models now where they create these rings without planets at all, what you're really seeing is the action of pressure bumps attracting particles into ring structures. Okay, so that's sort of the first part, trying to solve the very earliest stages of planet formation, how we get from these micron-sized ISM grains into maybe centimeter, millimeter-sized bodies. But the other thing that's really cool about radial drift is it gives us a natural way to explain the formation of planetesimals, and that's through something called the streaming instability. And I have to give credit here to a graduate student at University of Arizona, Urshin Lee, who made this slide and allowed me to show it to you. And this is, I think, one of the best cartoon illustrations I've seen of the streaming instability. And I know it still looks really complicated, but I'm going to try to go through it in not too long. So the basic idea behind the streaming instability is, you can think of it as basically being Newton's laws. So radial drift, right, I described that whole thing to you as gas dragging on the dust grains. What does Newton's law tell you about what must also be happening? If the gas is acting on the grains, exactly. Okay, you understand the basic physics behind the streaming instability. It's a two-fluid instability. So the gas is trying to slow down the dust grains. The dust grains are speeding up the gas. So normally, you'd think all the gas is orbiting at the same, say, roughly Keplerian velocity. But if I have a big grain here, the big grain is going to be moving faster than the gas. It's going to speed the gas up a little bit. The little grain, not going to do as good a job, right? The gas is doing a better job slowing it down. So I can create these waves in the gas velocity. And because there's this back reaction, you then get a little bit of a differential drift speed of the particles. And so the particles tend to naturally clump together. You don't need some underlying magical turbulent motion. All you need is to put particles in a gas and have Newton's laws work. And you will naturally get streaming instabilities out of a protoplanetary disk. So what happens if you put this in a hydrodynamic simulation is rapid clumping of particles. So what you're seeing in this movie made by Jake Simon is a shearing box where we've boosted into the co-rotating reference frame of some annulus in a disk. So you can imagine the star is here. This whole box is sort of moving around the star. And the color scale here is showing you the overdensity of particles. And so what happens is, because of this back reaction, you start to get a little bit of clumping. And as the clumps get denser and denser, ultimately they become self-gravitating and they form actual planetesimals, which can be hundreds of kilometers in size. And so we can look at, say, the size distribution that comes out of these simulations. This is mass relative to series mass on the x-axis. You can see what this means in kilometers up on the top of the plot. And this is just the number density per mass, again in units of series masses. And you see you get this wide range of sizes out, extending all the way up to a few hundred kilometers. And this process operates most efficiently if you can get higher concentrations of particles that are centimeters or decimeters, maybe even meters in size. And so we think this may solve that meter-sized barrier by basically just hopping over it, going from the small things that we think pressure traps can help us bring together all the way up to the big things. And when we look at our own Kuiper belt and our asteroid belt, it actually looks like the size distributions produced by these models are reasonably consistent with what's observed. So after this, the story is much the same, except for one crucial thing. So First of all, I just want you to keep one thing in mind, which is that if you saw this movie, right, these regions here, which are not the dense red dots, are not empty. There are still particles sitting out here. So this process of taking little things and making big things directly isn't 100% efficient. So the next phase was the one I talked about before, which was this gravity-assisted collision phase. So now we have these 100-kilometer bodies, and they start smashing into each other. And when they collide with each other, they grow bigger, and then they also produce these fragments. And so the really neat thing about the combination of these collisions and also the streaming instability making planetesimals is that you're left behind with this population of little small things, which are often now called pebbles. And this leads us to maybe another catchphrase you've seen, which is pebble accretion. And so the basic idea behind pebble accretion is that these large 100-kilometer bodies are actually really, really efficient at eating those small centimeter or decimeter sized bodies if you once again consider the fact that these particles interact with gas. So if I took my sort of plain old vanilla model of core accretion from the old days and I considered some growing planetesimal or planet core, and I calculated just based on the gravity from the star and the gravity from the planet, what kind of things could end up colliding and interacting and accreting onto this object, I would basically be left with these two little boxes here. And I would say only stuff at these velocities is able to make it down within the Hill sphere of this object. Things that are closer, somewhat counterintuitively, end up on horseshoe orbits. They sort of come close and turn back around in the rotating reference frame of this body, and they don't accrete. When you include the fact that there is gas drag, as we know is responsible for the rest of this radial drift, you can get much more complicated trajectories. And that's just what's shown here, is integrating these particle trajectories as they're coming in a disk, interacting with the planet, and spiraling in. And so if you do the calculation of how efficiently these growing planets can eat this material, it changes the growth rates dramatically. And so just look at these three lines here. This is a plot from a paper on pebble accretion from Lombards and Johansson in 2012. This is time measured in years. This is the core mass measured in Earth masses. And each of these black curves here show you how fast it takes something to go from less than a Pluto size all the way up to 10 Earth masses because it can accrete pebbles. And you see these time scales here are now hundreds of thousands of years or less, even out at 50 AU. And this is just an indication of how much more efficient it is for these 100-kilometer sized bodies to grow, not by having collisions with other 100-kilometer bodies or 10-kilometer bodies or 1-kilometer bodies, but by sucking these pebbles out of the background disk. For comparison down here, this is the classic calculation from the old core accretion model that says how long it takes to grow to, say, a few Earth masses. And you can see that the 50 AU line is off the chart, well beyond the lifetime of the disk. All right, so I'm 2 minutes. Okay, great. So just to summarize, if I go back to the sort of classic textbook problems in planet formation, our sort of modern solutions satisfy each of these problems. We think that growing to meter-sized bodies via coagulation, or even centimeter-sized bodies, is helped by particle traps. We no longer have to grow all the way through the meter-sized barrier if we form planetesimals from the streaming instability, and we can get around some of these very stringent growth timescale issues by considering the role of pebbles in adding mass to the cores rather than just gravity-assisted collisions. And in the last minute, I will just tell you why I think gravitational instability is not a great model for planet formation, even in the outer disk. So gravitational instability is a competition between pressure forces in the disk, gravity, and shear. You've probably all seen Toomre's Q. When Q is small, it means that self-gravity is strong and disks can be subject to the instability. I think it's helpful to write it this way, as some order unity coefficient times the star to disk mass ratio times the aspect ratio. When disks become strongly self-gravitating, you can sometimes get fragmentation into little blobs in the disk, sort of like the genes instability in a rotating reference frame. as the nonlinear outcome of the instability. Two reasons why this doesn't work very well for planets. Reason number one, remember how I told you that we barely have enough mass in the disks to explain the Kepler planets? So if you don't have enough mass to explain the planets, it's really hard to explain having enough mass to make the disk gravitationally unstable. In order to make this number about unity, I need this number to be basically 10 or less, and I need this number to be maybe 0.1, and if you multiply those two things together, you find that typical disks which have mass ratios of 10 to the minus 3 to 10 to the minus 4 simply can't satisfy this constraint. The second reason, just go back to this slide, is that if you calculate the typical mass that these objects form at, they tend to be a few Jupiters in size or bigger when they start. And then they are massive and can easily keep growing from this background disk. And so the combination of these two things makes gravitational instability maybe a good way to make brown dwarfs or other stellar companions, but it's pretty challenging to make most of the exoplanets that we've observed via this mechanism. So I will just skip ahead to my conclusion slide and take any more questions. Thanks. I'm not sure I know what you're asking. So what has been done with plasma models to map, how is the deep space probe travel related? That's the part I'm missing.
Can you predict where the
So we can't send spacecrafts out to other solar systems to watch planet formation in action, if that's what you're asking. Not yet. The best that we can do is use things like ALMA and JWST, hopefully, and WFIRST to take images, and we know where to look in the sense that we know that planets are forming in disks, and the disks are in young star-forming regions, so we can target the right sources. And even though I said planets move around, we know that they should be probably somewhere in the same vicinity as we see them in our own solar system, so we basically just try to look at those separations from the stars as best we can. Yeah, so a lot of the same general things should apply. I mean, we actually have, there's quite a few M dwarfs in some of those samples that I've showed you now. So we do have observations of the disks around M dwarfs. It seems that there is a rough scaling between stellar mass and disk mass, although some people will disagree with that because it's very hard to actually measure masses. So some of the things that might change are, say, the location of ice lines will change, and that might change exactly where you should expect to find pressure traps, and so you would maybe expect the structures to be somewhat different. The disks should be a little bit smaller, probably around M dwarfs than they are around G stars, so maybe everything's going to be a little bit more compact. But I think a lot of the basic physics should be same. I mean, none of these mechanisms are going to be very different in the sense that going from a solar type star to an M dwarf, you don't have a huge change in the overall mass, right? It's a big difference in physics, but not a big difference in mass, and so for a lot of things, mass ratio is really what matters, and it doesn't change all that much. So I guess what I was cautioning against is just taking an equation and randomly changing the mass without thinking about exactly what else is going on. I think it's going to be more important not for the details of the grain growth so much as the details of, say, magnetized accretion, where the sort of different ionization fractions you're going to get from an M dwarf spectrum versus a G-type spectrum are going to play a bigger role, but that's still a pretty open question. I don't think anybody has solved that problem for even solar-type stars. Yeah, so I'd say there's one reason why I'm skeptical that all these substructures are generated by pressure bumps, by planets, and that's because when we look at all the disks, we see a lot of these crazy, really large-scale structures, and what our theoretical models tell us is that you need pretty massive planets or multiple massive planets to create these gaps. And if we look at direct imaging surveys, microlensing surveys, and RV surveys, all of them tell us that there aren't that many giant planets out there on those orbits. So it's really hard to reconcile the statistics of weird things in disks with giant things that you need to make them. So I'd say that's one reason why there must be some role of dust being gathered in other places. But there's lots of really cool diagnostics that people are doing now. One of the most exciting ones, I think, is polarization with ALMA, because depending on the relative distribution of grains of different sizes, you get different polarization signals at different wavelengths, and planets versus things that aren't planets will give you different signatures. So there's some really cool work by Adriana Pohl starting to look at this now, so keep an eye out for that. I think that's one of the most promising mechanisms to probe that.